So far, we have talked about mechanical systems and chemical systems, and we've learned that linear, constant coefficient differential equations describe these systems in many settings. In both cases, and soon in electrical systems, external signals also can affect behavior. In mechanical systems, this is because of a force, while in chemical systems, it was in the form of accumulation. For instance, this slinky has dynamics that depend on the mass, so it oscillates at a particular frequency when I let it go, and it can oscillate when I force it like this. Now, the frequency of that oscillation depends on how I force it. Today, we are going to learn about the convolution equation. This provides us a notion of superposition with respect to external signals, like the one I just created with my hand for the slinky example. Let's assume that we have a single variable x and a linear, constant coefficient ordinary differential equation with a number. So we have x dot is equal to ax, where a is a number, plus bu, where b is a number, and then u is just some signal. The solution to this ODE is x of t is equal to e to the at x0 plus the integral from 0 to t e to the a t minus tau times b times u of tau d tau. This is called the convolution equation. Now, this is a pretty scary equation because it has an integral in it, but let's spend a moment to look at each component. The left-hand side of x is this term. It's just the exponential times the initial condition. This is the state evolution if there was no external signal u of t and is called the transient response. It should look familiar. It is just the exponential solution for the ODE when there is no external signal. The right-hand side involves an integral from 0 up until time t and does not include x sub 0, but it does include u. It is called the steady state response. How should we confirm that the convolution equation is actually a solution to the ODE? We simply plug it in and show that the time derivative is equal to ax plus bu. So we get d dt of x of t is equal to the time derivative of this, which is a e to the at x naught, and then plus the time derivative of this. And that's going to involve two terms. The first term is the integral of the time derivative of what's inside here. That's actually just a times 0 to t e to the a t minus tau b u of tau d tau. Now, the second term comes from Leibniz rule. So I have to take into account the fact that t is part of the integral, and Leibniz rule tells me that the result is e to the a t minus tau, where I plug in t for tau, times b u of t. Now notice that if I bring all this together, this is equal to a x of t plus b u of t. What does this equation mean? First, it means that we can separate the effect of the initial condition from the effect of the external signal. Secondly, it means that we have superposition for external signals. If I give you two signals, u1 and u2, you can find the state trajectory for each one and then add them to find the state trajectory for u equals u1 plus u2. To make this more clear, let's look at an example. Let's go back and look at the spring damper system from lecture 3, where we have an external force and we have an initial condition of x0 equals 0. So we have the wall, a spring, and a damper, and an external force. Let's assume that the external force is equal to sine of 2 pi t. This system has the ODE x dot is equal to minus k over b x plus sine of 2 pi t over b. Now, the convolution equation means that this ODE has the solution x of t is equal to e to the minus k over b t times x naught, we know that that's equal to 0 because x0 is equal to 0, plus the integral from 0 to t of e to the minus k over b t minus tau times 1 over b sine 2 pi tau d tau. Moreover, if we instead say that the external force is cosine of 4 pi t, this is now a 2 Hertz signal, then the convolution equation says that the solution to the ODE is instead x of t is equal to e to the minus k over b t x0 plus the integral from 0 to t e to the minus k over b t minus tau 1 over b, and now times cosine 4 pi tau d tau. Now what happens if the external force is equal to sine of 2 pi t plus cosine of 4 pi t? So if we have F external is equal to sine 2 pi t plus cosine 4 pi t, then x of t is going to be equal to, and I'm going to ignore the transient response, and I'm just going to look at the steady state response. This is equal to the integral from 0 to t e to the minus k over b t minus tau times 1 over b times sine 2 pi tau plus cosine 4 pi tau all times d tau. Now what is this expression equal to? This expression is equal to splitting this integral into 2 pieces. The integral from 0 to t e to the minus k over b t minus tau, 1 over b sine 2 pi tau d tau, plus the integral from 0 to t e to the minus k over b t minus tau, 1 over b cosine 4 pi tau d tau. But these 2 responses are exactly the responses that we got for these 2 signals independently. That means that you can get this signal either by reintegrating the entire system again, or by simply taking the solutions that you already had and adding them together. The convolution equation is valid for vector-valued ODEs as well, but then the e to the a term means something slightly different. So what should you remember from today? Remember that for a linear, constant coefficient, first-order ordinary differential equation with an external signal, the convolution equation gives us a type of superposition principle that includes both initial conditions and external signals.